All right, so let's start. Any questions about the project? How's it going? Pla Planning on starting tomorrow. I like that. Good answer. Everything going smoothly? Understanding things? So have you discovered the secrets of the architecture of SQL Server, the index architecture? What's different from the book? So what does the book assume is stored in the leaves of, let's say, an unclustered index? An unclustered index pointers to the data on disk, right? So it's like a disk address. What does SQL Server store in the leaves of an unclustered index? Yeah, so assuming there's a clustered index, what does it store? Excuse me. No, it's actually not a pointer to the page. That's really the interesting part. This is the discovery. You have to figure out what's stored. So, I mean, in a leaf, remember at the bottom of a leaf, let's see if this works now. Yes. You need a projector? Come on. This is a very secret drawing that I'm doing now, so you cannot see it. So I'm gonna make it a little bit bigger. So if this is a leaf of a B+3 index, what we draw in the book is something like, remember, we had the 5-star, and the asterisk was supposed to mean the addresses of all the things that have 5 as a key. So it's basically a key and a pointer, which is like a page ID, and then maybe a slot. This is really where you find it on disk. SQL Server does things differently. And so you should have discovered by now the secret of this. So anybody figure this out? So they do have the key, of course. You need the key to search. But then you need something to identify the record. Any? So have you read the help? No? Nobody? All right. All right. So basically, here's a hint. This is not it. And for the first part of the project to figure out what's here. How do they find the record? Yeah, it's a pointer to the clustered index, which is basically the value from the clustered index. What's the benefit? Well, the benefit, so for example, if you have an ID, clustered index on an ID, this is going to be your ID. The benefit is that this doesn't change. Even if you change the location of the thing on disk and you reorganize the clustered index, that thing actually doesn't change. So there's no need to rebuild the unclustered indexes. So that's the benefit. The drawback, what's the drawback? You need to go through the, so you already went to the unclustered index, but now you need to go through the clustered index. Excuse me. So that actually can be a source of extra IOs. So that's the drawback. Now, assuming the cluster index is not too high because data is already in there, then it's not maybe a big cost, but there's some cost. So this is the answer I'm looking for. It's exactly this. So there are interesting things that can happen. For example, if you have a query that's looking at the key and the thing from the clustered index, you might actually be able to answer that query directly from the index. So in this particular example, we have select, let's say, unique 2 from the Wisconsin relation, and then you have where unique 1 is equal to 20. it turns out that the unclustered index is actually covering this query. This is the search key. This is what you use in the unclustered index to look up. And then you're actually storing this value, the unique 2 value, inside the unclustered index. Yes, yes. Anytime you need something that's not a part of the search key, then you would need to go to disk and actually retrieve the record. So there you have this one exception. Of course, if you were selecting unique 3, it's a different story. Then you take the unique 2 thing that's in the index, that's here, and you go through the clustered index, you retrieve the record, and you find the unique 3. But if you're looking at unique 2, it turns out to be a covering index. And you can try this. I mean, you can do a query like this with unique 2, and then see what does the plan look like. And it should basically answer that directly from that index. It should just be a single index lookup. Yeah, partly. So basically, unique 3 means that everything you do, you have to go and actually get the record. So this avoids doing things like using the index X covering indexes. Yes. And so I mean, at some point somebody was doing. So let me erase a little bit just to get some space here. So at some point somebody did the measurement with a query like this. Select unique 1 from Wisconsin, where unique 1, and then there was a condition or something like this. And they basically conclude, or there was a range somewhere. So they concluded that using an unclustered index was much faster than using a clustered index or a sequential scan, up to 100%. And they happily reported this in the report, and they got a pretty bad grade. So because you can obviously see that this would perform very quickly, right? You're looking at unique 1 in the index, and you just return it. That's it. No going back to disk to retrieve anything else. No, nothing. Because the unique 1 is already in the index. You know what it is when you're scanning through the index. So you just return it. And so that's again the difference between a covering index and a non-covering index. So by using the unique 3, we basically avoid covering indexes every time. Yeah. So what we did is we have a count, and that's basically to avoid sending lots and lots of stuff over the network onto screen. So to avoid putting that into the measurements. We could do a count star, but a good optimizer would figure out that unique 1 would actually satisfy as a count star. So this is therefore we use count unique 3. And so there was I had a interesting optimizer story from at some point. So basically I think there was Informix that had a feature that if you counted from a particular index, if you said, let's say you said count unique 1, which has an index, it would be very quick because the index number, the count was actually stored in the index. So just go to the root of the index, find the number, and return. Yeah. So is this indexing tree unique to a SQL Server? Basically, Oracle has something called index. Has index organized tables, and that's very similar to this. And if you have an index organized table in Oracle, then that does affect the unclustered indexes. But I think SQL Server is unique in storing the primary key or the clustered index key. I think they are doing similar to the book, basically. Yeah. Yeah. So, but to conclude the story, that this optimizer, if you asked for a count of a particular column that had an index, then it would do that quickly. If you said count star, it would basically go and scan everything. So, and it wouldn't figure out that you could use one of these indexes, any one of them actually, and it will still work. And so sometimes you have to play with your optimizer a little bit. Anyway, so that was basically the first part of the project. And now you have to go and read a little bit on this. But this is really the difference. And it turns out in exceptional cases, it turns out to make a difference, significant difference. But yeah. So, and then, if the search keys are long, or no, if the clustered index is not unique, then SQL Server will basically do something else. It will create its own record to find it. But because you cannot uniquely point to a record if the clustered index is not unique. If you cluster the name, for example, then it basically has some kind of row ID to go through. Yes. 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 Right. Yeah. So well, no, I mean you would basically have to retrieve every record from the clustered index, and if you're not careful with the order, then the clustering doesn't help, because you will have to go through different places in the index. But remember the technique that we talked about a little bit when we reordered the reads, when we took the ID, which would then be the key of the clustering index, and we ordered that, and then we went and retrieved. And so if you're retrieving, in particular, if you're retrieving many records, then you would actually get kind of a sequential performance out of that. So I think this is what you were sort of alluding to, and this actually SQL Server does that. So the question is, when does it decide to do? So it basically evaluates, estimates the cost of both approaches, and when the cost of doing the reordering reads is smaller than the cost of going directly, then it switches. The question is are the estimates correct? If they're not, then you'll see a drop. If the estimates are incorrect, then at some point it makes a suboptimal decision. And in that case, you will see it making basically, you might see it going up and then a drop. And that means it should have made the decision earlier. So that was another puzzle of the of the project. Have you seen this behavior? It didn't do this? Okay. It's smooth. Okay. Yeah. So basically, the optimizer, basically at some point like this, it makes the decision to switch. Now, depending on hardware, you can either have this or you can have this. It's really going to depend on your hardware, because the cost is, I mean, it's a very general model that is not specific maybe to your computer, but it's a general model. And at some point, I think the cost of one is 1 second on somebody's machine at Microsoft at some point in time. So that's what they said to one. Actually, I think the guy was called Joe or Bill or something. They actually named the guy, the developer that created the unit, which was 1 second on his hardware, at a given point in time. So it's basically euros, or whatever currency you want. Or monopoly money. It doesn't matter. The unit is nothing. But depending on your hardware, the costs of CPU versus disk vary, and so you will have decisions that might be slightly off. And again, this is an example. So I know some people got this, where the optimizer basically made the wrong choice. It's setting the switch here when it probably should have been roughly here. So given this. Yeah. So in that case, basically your hardware somehow, in this case at least, matches the assumptions that the optimizer makes. Okay, so you found the exact value. Okay, okay. So by trying to create the dip, you basically pinpointed the exact value. And what is it? 130,900. Yeah. Okay. So 13%. Yeah, 13%. Okay, interesting. Okay, so you can actually check, the rest of you, if you see the dip, you can check whether the dip is at the same point. Yeah. So this is kind of interesting, right? 4% reordering. Okay. 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 That's interesting. All right. So anyway, so I hope you're making progress, measuring, understanding. The key to this project is the understanding. You measure to understand. You don't measure to give me numbers. I've seen the numbers. You measure to understand and learn. If you learn from this project, this is key. That's what you need to do. And then the other thing actually I would like to learn from this project and this course is that if at some point you are not sure about the best way to implement something, go and implement both and try. You will never know until you try. And so try to make like simplifying assumptions, do some, assumptions about distribution, and then maybe create data and run things and just see. And then like you were doing, you were finding the spot. It is knowledge that you know. Now you know this. And it's interesting. So, and some people in industry actually do this. And these are the good people. These are the people that really, when they have to make a decision later on, they can make the right decision because they actually test it. So, and for example, Grímur, that's going to teach the second part of the course, he's a type like this. He will just go and measure and make both things and measure and see. And so in many cases, he just knows. Should I do this or that? Well, in this case, this is better. In some other case, that might actually be better. Anyway, so we were starting to talk about join methods. Did the selections, indexing, any questions about that? Selection processing? All right. So then that's one thing that gets done very frequently. The other thing is joins. And basically, because you went and normalized your database to pieces, then the system is going to have to join tables repeatedly again and again. And so this is most of the time spent in databases actually on join processing to some extent. And so the question is, how do you do this? And there are basically some brute force ways which just read everything to with varying degrees of reuse of pages. There's an index nested loops join which reads one table, looks up from the other from an index. And then the sort merge join, which sorts both inputs and merges, and then hash join, which either hashes one input and probes, or if you have large tables, it will hash both and to partition. So we'll go through this in detail now. And so the examples we're using is typically an equijoin, which is, we'll talk a little bit about the about more general joins later on, but if join processing is most of what we do, then equijoins is most of the join processing, because you always have these key and foreign key relationships that you're joining together. So from algebra, you will remember the cross product, basically creating all the tuples that or not matching each other, but just cross multiplying the two tables and then selecting. And we cannot do this, basically. It's too big. If you have 1,000,000 records and 1,000 records, that's 1,000,000,000 records in the cross product. So we really need to do the processing early. When we do the formulas here, we basically omit the cost of writing the results. So all the formulas are skipping that. And we have a join that's selecting everything from reserves and sailors on a key foreign key pair. Reserves has 1,000 pages, so it's a bigger table, 40 bytes per record, so 100 records per page, and sailors 50 bytes per record, 80 records per page. So this is sort of when we do calculations, these are the things what we do. Okay, so a nested loops join. It's basically very simple. For each tuple in one relation, we go through the other relation, and if their search key match, then we add them to the result. Fair enough. Just you can see the program here, pseudocode. This is what we do. So there's an example. All right. So nested loops join. So two tables. We used this in an example earlier. We have sailors, we have reserves, and you can see sailor 28 reserved two things, sailor 31 and 58. And so we want to find all the matches. So we just start with sailors, read one record into memory, and then we start reading reserves. No match, no match, no match, no match, no match, no match. Done. Go to the next sailor. And we read again. Now we actually found some matches, right? 8, 28, no match, no match, no match. Go to 31. We again find some matches, we output them. Go to 44, go through the relation, no match. Go to 58, we find a match. What was the main characteristic of this demonstration? Reading the same thing again and again. How I did a lot of this, right? Pressing the spacebar. What does that mean? Many IOs, right? So it's just reading everything again and again. And now, the worst thing, of course, is we read this only once. It's not too bad. But we read this basically for every record, we read this once. So that's pretty bad. And you can probably very quickly think of ways to do it better. If we go back to the slideshow. So the cost in this formula is basically M, which is the smaller table here. And then we need for every page times the number of records in the page, we need to retrieve the other table. With me on the cost formula? And so this comes to 1,000 pages, and then 1,000 times 100 times 400, which is a lot of IOs. Basically 6 days, reasonably. Maybe a slightly slower, less now. Now, can we decrease this cost? We could maybe decrease it a little bit by switching the relations, right? So one of them is 500 pages. So, and that basically would mean fewer scans of the 1,000 page. So you can just switch here. Because remember, joins are commutative. The order doesn't matter. So you could basically switch the order. In that case, you would have, no, you would have, or not. Okay. You would have n plus n times ps times m, which, you know, this is 80, this is 500, this is 1,000, and this is 500. So this would be how much? 40,000 times 1,000, that's 40,500,000. Slightly less. So maybe only 4 days. Anyway, so the obvious way to improve this is something called the page nested loops join, which, remember, the here we basically completely ignore the pages, right? We just loop. So you could think of having like a loop within a loop, say, for each page in R, and then for each page in S, for each tuple in the page, for each tuple in the page. So like a doubly nested loop. And that way you will only have to read each page once, so you get rid of this factor, basically, right? Still a while, but it's slightly better. Can you think of using buffers to do this even better? Yeah. So basically, this is called the block nested loops join, which is grouping the pages together and reading blocks. And then you're comparing blocks to blocks, and this is faster because you do less IOs. So this there. So let's talk about index nested loop join first. We'll get to the block, but this is exactly the idea. You improve the IO usage. So the index nested loop join, you can basically think of, rewriting it where you are just selecting all the records from run relation, and then for each record, you actually go and find the match through an index. So let's say you have all the sales records for a company and you want to join with the customers. So you go through the big sales record table, and then you take the customer ID and you go through the primary index of the customer table to find the record. And you add the columns. Clear? This is kind of a typical way to use an index. So we have an example. Yeah. So basically these are the queries and there's an index here. And we do the same kind of thing. We scan this relation and then we, instead of looping through, we actually just go through the index to retrieve. So 22, we go and look for 22 in the index. There's no match, so we're done. We actually didn't read the table at all. 28, we go through the index, and then we find the first relation, and then we have to keep on scanning through the index to find the next, and return both. And then we will basically try the next relation here, the next record here, find that it's not 28, and then we'll go back to 31, retrieve, done. 44 doesn't find a match, 58 finds a match, and we're done. That was that was a lot faster, right? So at least for what I'm doing. So for every record here, you only had to go through the index, which is less of a cost. Now, it turns out that this isn't used very much. It's mostly used when there's some other condition that makes the result set small, because looking up through an index is typically fairly expensive. And so if you're, for example, if you have a whole relation to join, you would basically never do this. You would always create a hash table for the customers and use that for the sales, join with the sales. But if you, for some reason, you manage to find, you were only looking for sales record for, very few sales records, then actually joining with the index might be good. So if there's a filtering condition on the source table. Now, if you have an index on R, then of course you can switch. That'll be easy. So if this is the sales tables and this is the customers, then it makes sense to switch. And so because the joins are commutative, this is fine. And again, how do we know if we should use an index? How does the system know? Any? Excuse me. Yeah, first it's going to go through the catalogs and find out whether there are indexes. Once it's done that, how does it know whether to use them or not? Who's doing this? The query optimizer. Exactly. And the query optimizer is basically looking at this plan, saying, what is the cost? It's looking at nested loops join, what's the cost? It's looking at hash joins, estimating what's the cost, and so on. For all the join methods that it has, it's going to try to estimate the cost of this, and then just pick the cheapest one. But this is, we'll go through this on Thursday, then we'll look at the query optimization. So the cost of the nested loops join, index nested loop join, is this formula, which is a little bit ugly, but go through it. So it's basically first, So I think when I switch to a second slideshow, it actually stops, the pen stops working. So this is the cost of retrieving one relation. And then for every record, so this is every record in that relation, you need to look up an index. And remember, the index had two costs. One is traversing the index, and the second one is retrieving the actual records. And we went through that last time. What are the costs? So B+3, there might be 2 to 4 IOs. And if you are looking for a single record, then that's going to be 1 IO typically, unless some clustering comes into effect and so on. Yeah, so that this actually says here. So, clear? Is this formula roughly clear? Now, if I have some conditions on this table, something that reduces the number of tables, then the number of records, then basically this affects that part. If there's a selectivity, you might actually multiply this by that selectivity. So if you have a condition, for example, let's say a simple condition on gender, half women, half men, then this would be half. Selectivity would be half. If you have a condition on salary, you're looking only for the people with the very highest salary, then maybe selectivity could be 1%. And then that goes into the formula. Okay? Right. So there's a couple of examples of how to do the computation. Here's the join. Remember, we're joining reserves and sailors. There's a hash index on sailor. And in that case, we have to read the reserves, which is 1,000 pages, 100,000 records. Then each record will join to one record from sailors because the SID is a key. And so 1.2 IOs to read the index and 1 to retrieve the record. And then you can do the whole calculation. This is 220,000 and this is 1,000. This is what you would get from the cost formula. If we switch, there's a B+ index on reserves. Then you would read sailors. You get 40,000 records. And each record in the reservations joins to 2.5 on average. How do I know this? How do I know that each sailor makes on average 2.5 reservations? Yeah, discount the relation. So we have 100,000 reservations, 40,000 sailors. Do the division. And so this gives me, normally, let's say there are the root is in memory, we get 2 IOs to traverse the index. We get, depending on the cluster, we get one number, on unclustered, we get another number, and then we just calculate and add. So it's just putting numbers into the formulas. And this is something that I expect you to do, be able to do. Put numbers into formulas, choose joins, for example. All right, so how could we use additional buffers? This is exactly the idea that came out here, is basically to do blocked IOs. And this is a special case, if one table fits in memory, what do? We just read that table into memory, and then we take one page or a block of this and compare to everything. And then we take the next block, compare to everything. So in that case, the cost is actually n+n. If one relation fits entirely into memory, the smaller relation, then we can just read the larger one and then compare that to everything. Clear? And this is the same trick used for hash join. If one table, the hash table for one of the relations fits in memory, then we just need to read once. But then we have basically, the other thing we could do is to read in chunks of both relations and do the join. And then we try to read in another chunk and do the join here, and so on. So I think I have an example of this. Yeah. So this is the block nested loop join. we basically try to read from one table as much as we can, and then we compare the other relation to that. And then we read the next chunk and compare the entire relation to that and so on. So let's get an example. So we have the same join, and we assume we can fit 3 records into memory. And so what we do is we read them into memory, and then we just go through this table and we're comparing that to this side. You can see the showing the matches. We go through that, then we read the next chunk into memory, and we loop again. It's a block nested loops. We read blocks from one page, from one relation, and then we go through the other one. So, any questions at this point? You look stunned. You have a deer in the headlights look on you. And we haven't gone through the complex ones. We've only gone through the simple ones. So, yeah. So let's take a break now. And I think, well, actually, no. Let's do the comparison, then we take a break. So this is the cost of the block nested loops join. It gets a little bit complicated because we have to calculate the number of blocks, which is basically how many pages can we allocate. Here is the block size and then pages of the relation, and that gives you the number of blocks. Not hard. And then you read the outer, and you need basically to read the inner file for the number of blocks times. So, and if we do a comparison of this, for the particular parameters that we're using, then maybe we got 6 days, we went with page nested loops, we went to 1.5 hours. For index nested loop join, in the tens of minutes. For a block nested loop join with more buffers, on the order of minute. This is making some assumption on IO cost and so on. 12 milliseconds, I think. So, actually probably 10 milliseconds. Anyway, so you can see that, as you go down in this list, for a whole join, doing some kind of block that is doing IO optimization turns out to be the best thing. So let's take the break now, 5 minutes, and we'll start 6 minutes after. All right. So we had an interesting discussion at the break, basically thinking about when would you use an index int, and one question was, could we use an index int to avoid optimization? The answer to that is no. Basically, the optimizer will be started. It will take the index int and use that. You might limit the generation of plans a little bit. But basically, if you know that the optimizer is making a mistake, if you know that it's suboptimal in some cases, you just know better, then that's when you use an index int. And the other thing is, can we avoid the cost of query optimization? And the second question actually is the cost of query optimization significant? And the answer to the latter is, if you have a query that's going to run for 6 days, then cost of optimization is very insignificant. If you have a query that's is basically a single lookup in an index, then the cost of query optimization could be significant. And in the latter part of the class, you look at ways to avoid query optimization. Basically, it's called plan caching. So if you write your query in a specific way, the system can look up into the plan cache and find the old cache and reuse it. And sometimes that's a good thing. Sometimes you then get stuck with the first plan, and that might be suboptimal in some cases. So it's a thing that you would use wisely. So interesting discussion. So basically, going back to this table here, we observed that for the very simple join that we're doing, the block nested loops join is much faster, right? So the question that arises, why would we ever use these? Would we ever use a nested loops join and a page nested loops join? Would you implement that? Probably no. Now, so these are mostly for interesting purposes. Now, if you were writing a new database system, actually you probably would do this first, because it's very simple, just to see something working, but not later. But the question is, should we ever use index nested loops join? And so the answer to that is, if we have additional conditions on the what I call the outer, which is the first thing that gets read, that means fewer index lookups, and so that could be beneficial. If we have to scan the whole outer relation and then just look up a few things, then that could actually be very cheap. So, and also, if you have a computer with limited memory, that might be better than a block nested loops join. But basically, the point is we must avoid the very bad ones. So, any questions on the nested loops thingies? So we get to actually come back to this a little bit towards the end of the lecture. Now, the sort merge join, we're getting now into the more efficient things. The sort merge join is basically, it's very simple. We sort both inputs and then we merge. So I'm going to show you an example of the merge, just so that you can see how it goes. And in this case, we're lucky that both inputs are sorted already. That means the sort part of the join is done. and we just have to merge. And the way the merging would go, just in case you didn't notice, the way the merging would go is basically we start by reading the first thing from each sorted relation into memory, and we compare. We find that they're not equal, so we have to basically progress. And the way we progress is that we pick the relation with the smaller value, smaller key, and we get the next thing. So in this case, 28. Now, 28 is matching, so we return that. Now we have to progress, and in this case, because this is not unique, we would progress on that. If they're equal, we progress on the not unique. So we get the next one, and then the next one. So this is a match, this is not a match. Okay, so now we have 28 and 31. We take the smaller one and we advance. And now we have a match, we have a match, we have a match, a match. Progress in the smaller value, 44, 58, we have a match, and we're done. So that's the merging part of the sort merge join. Now the sorting part, you know very well, right? We did that last week, so we don't have to talk too much about this. Yes? Yeah. So the question is, could if you have limited memory and so you need to store the sorted things on disk, are you then doubling the storage? Yes, you would be doubling the storage. Yeah, just for this query. Now, in some cases, it might make sense. Now, obviously, if you have a clustered index on one of the IDs, you avoid the sorting. So that's one way that you can do. If you're lucky enough that both are sorted, then this is very fast. If you have additional selections, then you can apply them on the fly before the sorting, and that reduces the content, the disk space. And then, I mean, basically, we'll figure out that if you have one extremely large record table and another small one, then you use hash join anyway. So this turns out to be better when they're sort of equally sized. So we'll get through this, but yes, you would be using a lot of storage basically. But in a database server, this is basically temporary space that then gets thrown away. So what's the cost of this? Well, it's basically the cost of sorting, which is roughly m log n and n log n. We had the precise formulas before, and then you need, assuming that these things get written to disk, you then need to read them and do the merging. So this is the last part here. So, that's the last part here is to read the final output things, the final sorted thing from disk, and then output this. And with some assumptions, 35 pages, you can sort both in 2 rounds. That means to sort R is 1,000 pages times 2 rounds. Sort S is 500 pages times 2 operations times 2 rounds. So that's 2,000 IOs and 4,000. And then read everything is 1,500, and you get 7,500. So this is comparative with the block nested loops join, but you can observe that block nested loops join needed 100 buffers, and this one needs only 35. So again, from formulas, you have to go through this. So I'm gonna, so we'll go through the buffer requirements in a bit. So that basically you can see that the sort merge join for this very simple thing is very competitive. It's using fewer buffers, similar cost. So how can I do how could I figure out the 35 pages? You can basically try to figure out how much you need to Actually, I'm going to do this on Thursday. I need to prepare a little bit because I will mess this up if I don't have it in my head. So we'll do this on Thursday. We'll talk about the buffer requirements. It turns out that if you're smart, we have this optimization. If you're smart, then you can avoid writing the final sorted things. And that's the trick we have to do for short materials to avoid storing the thing. We do have some temporary storage because in the first round, you're creating sorted runs, and those are actually you have to store. But then if you're clever, then you can avoid doing the final write. Now, this is still slower than block nested loops join. But it turns out that the block nested loop join is very sensitive to the buffers. So the more buffers you have, the faster it is. Whereas the sort merge join is much less sensitive to this. So that's another win for the sort merge join. And so this optimization that I mentioned, basically if we can fit intermediate results into memory, then we can essentially go through one relation and we create the sorted runs. And then we go through the other relation and we create the sorted runs. And then what we do is we read this into memory and this into memory, and we do the merge. Because they're sorted, so actually no, we read the first part of everything, sorry. First part of everything into memory, and the first part of everything here into memory. And then we do the final merging at the same time. So we don't produce the sorted outputs. We just sort of half sort it. So if you haven't read the book, I would recommend to read this, and then I'll talk a little bit more about this on Thursday, because it takes a while to get your head around this. But the trick is basically to avoid the final sort. And that with this optimization is slightly faster than the block nested loop join. Now, can we use indexes? It's the same as with sorting. If you have an unclustered index, terrible. If you have a clustered index, really good. Same thing. Covering indexes, if you have all the columns you need in sort order, then you can just read the index, and it's beautiful. If you have all the columns but not in sort order, then you actually might read the index and sort the values rather than read the relation. You're following? So don't go to the relation to read it, because that might be big. Just read the index, which has all the values you need to sort. So even if the covering index is not optimal, it could still be useful. All right. So this is the sort merge join, and then we have the hash join. And we talked about this a little bit earlier. It's basically the basic simple hash join is to take one relation, create a hash table, take the other relation, and probe and look for matches, and return. So that's a simple thing. What is the cost of this? You need to read one relation into memory, and then you need to read the other relation and probe. So this would be very cheap if you can do this. If you can fit a smaller table into memory. It turns out, again, because we are very often dealing with a few, one very large table and then some small tables, that it's very typical that you can fit all the small tables into memory at the same time. And in this case, the hash join is extremely fast. You just read them, create the hash table, and then you take the large table and you just probe all the hash tables at the same time. And it's fast. Do we include the hash cost? No, basically, in the cost model we've been using, then we've been assuming that CPU is free, which is not true, obviously. And the SQL Server does account. They have a ratio of CPU versus I/O. So, but in the simple model that we've been working with, then no, we just ignore that and just count I/Os. And we haven't even made distinction between sequential and random IOs. So it's very rough model with SQL Server again does. We try to make that distinction. So for example, in this case, these would be sequential IOs. In the case of the index lookup, that could be random IOs. So, but are you with me on the simple version? Now, if the smaller table doesn't fit in memory, then you need to do something called a double hash join, which is basically you have first a partition phase, which takes the relation and partitions that basically using hashing. So it has a hash function and has some buckets, but the buckets get streamed to disk. And you do this for one relation and then the other. And after that, you basically take each bucket from R, and you take the corresponding bucket from S, and you do the join on those. And the reason this works, again, if we're assuming equijoin, assuming equality, is that whatever goes into this bucket in S is going to go into this bucket in R, because we have equality. And we're applying the hash function on the columns that are in the equality condition. An example here. Let's see how that goes. So it's again the same join, same tables. First we partition one of the tables. So we have again the horrible function sit modulo 4. Nobody can ever do this in real life. So we take the first one, modulo 4 is 2, next one modulo 4 is 0, and so on, and we just fill the hash table. And these buckets are actually on disk. So this is not just in memory, it gets written to disk. So again, doubling the space requirements for the table, just temporary stuff that we need to store on disk. But this is the way to do the join, because otherwise we can't fit it. Then we partition R with the same hash function, and then we do reserve. We do the partitioning. First two go to bucket 0, the next 3 go to bucket 3, and then to bucket 2, and we're done. And this is on disk. So typically you would have a buffer in memory, and then you put things to disk. And so we have a current status with beautiful drawings. And you can see basically the matches are all between buckets. And this is not a coincidence. This is, again, because of the hash function that's applied on both sides of the equation. The same hash function on both sides. So you're guaranteed that the matches will be in corresponding buckets. So then all you need to do is to basically do a simple hash join with, let's say this as inner and this as outer. So you read this into memory, probe. Read this into memory, probe. Read this into memory, create a hash table, probe. Yes. Do you have need? So basically, you need to be sure that this hash function here, we call it hash one, is different from the other one, because otherwise everything here would go to the same bucket. So everything in this, because if you apply the same hash function, then basically this would be in one bucket and nothing would be in any other bucket. So you really need to make sure that they're quite different. And there's probably a good theory about that somewhere, but this is really the key to make sure that the distribution is good. Now, what's the worst thing that could happen in hashing? Everything goes into the same bucket. What might be the reason for that? Or, a lot of things go to the same bucket. If you have few employees, yes. Right. So if one employee is basically your big sales star and is selling everything, then in one of the tables, that employee would basically, you couldn't separate that. You would always go to the same bucket. So in that case, it's a matching join, but basically, if one of the buckets is too big to fill in memory, then you wouldn't be in trouble. Then you cannot take that in and do the hashing to create the different tables. It would basically never decrease. And so that's a kind of a degenerate case, in which case, if this happens, then SQL Server, for example, would just sort to sorting. If it finds out that the distribution is really bad, it will actually go to the sort merge join. And it could do that within a single bucket and then do hashing for all the others. And that would be fine. You could sort these things here, the bucket 2, and do the sort merge join for just that and do hash join for everything else. And that would work out fine. But the degenerate case is when you have really bad distributions, everything goes to a few buckets or even a single bucket. And in that case, hash join is, turns out to be more expensive than you expected. So again, this is just to show the join phase. You have these bucket 0. You read one of them into memory and create a hash table with modulo 3, which is a completely different function, much better. Just kidding. And then you take the reserves and you use that to probe the hash table and return the join. So that's, now you're into the simple join. And so the double join is to break down the relation into parts that will fit for a simple join. What if you have a really, really, really big table? Like horribly big. Maybe you do a triple hash join. So you partition, you take each partition, and you partition that, and you take each of those partitions, and you do the join. Just need to break it down until something fits into memory. And then you can do a simple hash join, and you're happy. So, and I don't want to do this. And so it turns out the memory that you need to do a double hash join is the square root of the smaller table. And you can ask, why smaller? It's the same thing as with the can you do a simple hash join? You can do a simple hash join if the smaller table fits into memory. And the square root, basically, when you do the first partitioning, you will do partitions to the square root of the size, and then because you need square root of m pages to fit the buckets into memory, and then you can do the square root of you can fit each of them into the memory. So again, I'll go through that. I'll go through the square root thing on Thursday. I recommend to read the book. I suspect that most of you haven't done it, looking at the faces that I see in front of me, but I may be wrong. But go through that, and then the square root effect is pretty important. So I'll go through that on Thursday. Now, if you have a hash index, you can use that. And because the hash join is looking at the smaller table, it's actually more memory efficient. So hash join, for example, with 25 pages can do the same thing as merge join can do with 35 pages. With 500 pages, you can do the simple hashing. Just fit one thing into memory, and you can scan everything. So if you look at the block nested loops join and the hash join, this is basically sort of the comparison. A block nested loops join will compare everything to everything eventually. We'll just do it in blocks. Whereas the hash join will do the partition and then just compare the buckets. So this is sort of a depiction of that. If you can fit one table in memory, it's pretty much the same algorithm. It's just reading the whole thing into memory, creating a table to look up, and then going for it. But hash join is pretty good with large tables, whereas the block nested loops join isn't, because it's repeatedly looping through a large table. Now, sorting versus hashing. So basically, sorting is slightly more versatile. Hashing is generally faster, and in particular because you are using the memory requirements of the smaller table. For the sort merge join, you have to sort both, and so the memory requirements are actually of the bigger table. And in a typical database that we talked about, when you have a huge table and some small ones, then hash join tends to win. But sorting is good with skew. Remember when you have situations where everything would hash to the same bucket? Sorting doesn't have that because it's just sorting everything and then doing the merging. It will give you order. So if you're doing an order by, or let's say you're joining two tables and the third table is actually something that you want an order on, then this might be better. So because it gives you some order. And what you can see is that in the sort, basically you take the thing we call this physical partitioning. You just say, start with creating these sorted runs. And that means I just take the first things in the file, and that's my partition. I take the second things in my file, and that's my second partition. So it's not looking at the data when it's partitioning. It's just looking the way things are organized on disk. That's what we call this physical. Just takes the first, it fills the memory. So let's say the memory has B, so it takes the first B blocks, and that's your first partition. And then when it's doing the merge, that's when it's looking at the data and comparing. And so we call this a logical merge. The hash, when it's doing the partitioning, it's actually looking at the data. It's doing the hash function on the data. And so it's grouping together things that are related. So that's basically logical partitioning. And then at the end, you basically have the merge, which has everything that's related. And then you can do sort of the physical thing. You got the group together, and doing the join is simple. So it's called a dual operation. And there are, typically one of them is better than the other, and depending on these situations, you can see when they're good and when they're bad. So it's kind of interesting to see the similarity. And it turns out in some database systems they actually implemented very similarly. So it's interesting. Now, so we talked about equijoins. Arbitrary joins, meaning that you say, joins where one column is 2 times another, or where, something is bigger than something else, or not equal to, or whatever. So these are kind of arbitrary conditions. Now, so that's the inequalities and ranges. Actually, if you have equijoin on many columns, that's kind of simple, right? You can do a hash function on all columns or a sort on all columns. Doesn't matter. But here, for example, when you have inequality or a range or not equal, you just can't use hash join. Why can't you use hash join? Yes, yeah. So the hashes are randomly assigned to buckets, and meaning that there's no order or anything. So ranges fail, not equal, then you have to compare everything to everything anyway. So it's, it doesn't work. So using an index or sort merge join can be appropriate. I mean, with ranges, it might be good, for example. If you're doing ranges or, between, then having a sort order might be pretty good. But block nested loops join will basically work for anything. It really doesn't matter what you supply the block nested loops join with, it can do anything. So that's the most versatile thing. So this is why the first method you would do is some kind of nested loops join, because you can give it any kind of condition and it will implement it. It will evaluate it. What would be the second join algorithm you'd implement? Hashing, I guess. because it's, there are so many cases where it's efficient. So, but basically that's, you get something that is very complex, that it's not, not equality and everything, then, you'll just try, and you can try this on SQL Server. You just give it some nasty conditions and see what it does. It's probably going to give you block nested loop join. So that's the join. And this is really an important part of what you learn here. Understanding these trade-offs really can help you when you go into industry and you're trying to figure out what the hell the system is doing and why it's performing like this. See, looking at the query plans. I mean, there are people out there that really don't know what hash join is, and I found them to be at a great disadvantage. So this is, really something that I want you to take back from this course. Now, set operations, that's the last thing to talk about in this. Basically, you can sort of think about them. I mean, they're kind of similar to joins. Intersection, for example, it's basically a version of a join. How is intersection related to a join? You're looking at things that match on all columns, kind of a join on all columns. You take two inputs, and the things that are the same in them, you have to return them. And so it's very similar to a join on all columns. The union and difference, they're very similar to projection. So, for example, if we look at the union, we can do this with sorting by sorting the tables on both columns, and then we do kind of a merge. So the only thing we have to do in the merge is to remove duplicates. Can you try to visualize the merge? You're looking at two things that are sorted, and so if you do kind of the balancing act that we did before, going down when you have when they're not the same, then you take the smaller value, advance that. When they are the same, you output something. And then you just need to take care that you don't output duplicates. So it's really exactly the same as a sort merge join, except the merge process is slightly different. Hashing, you can partition R and S, and then for each partition, you build a hash table. And from the other relation, you probe, and if you find a match, you put that to the output. And then you actually delete it from the hash table to avoid duplicates. So that's part of the assignment for tomorrow, is basically to talk your way. So a talking assignment. So whether there's some questions, how would you implement things like, I think we talked about union or intersection, and talk about these issues, and then you do a small write-up and you're done. And you should do it in 90 minutes. If you stop, if you haven't done it, then just stop, go and finish your project, and then come back to this. They're interesting questions. You should understand every one of them. But today or tomorrow, you just use 90 minutes, see how far you get. All right. So you're probably a little bit lost now. It's a lot to take in. But now we've gone through this, go and reread things in the book that you found to be particularly difficult. We'll look a little bit again at this probably on Thursday. And of course, when we start talking about query optimization, what the query optimizer does all the time is taking these formulas and calculating costs. So it's always looking at this. So it's important to get that in. So try to find some time to look at some of the most complex things that you've found. And then we'll see you on Thursday. All right.